Hi, my name is Sean Pierce, and I'm here presenting my malicious macro document classification AI project. All the source code and the models are right here on my GitHub. So most cyber incidents involved email-based phishing. In 2021, the average click rate for a phishing campaign was 18%, and Verizon in 2019 reported that 94% of all malicious email attachments uh, contain malicious word macros. Now, Symantec says 48%, so I think that's a bit high, but the solution, or at least part of the solution, can be leveraging fast, scalable models to classify at least very malicious documents, at least produce low false positives or low true positives to help with some of the scalability issues in catching malicious macro documents. So the background for this is that this open source project called MMBot with the source code right here on GitHub uses a lot of these techniques. Now, I re-implemented a lot of this, used a lot of the same features, and added about 80 times more data. And in this presentation, we'll be referring to this as the old model. For my corpus, I downloaded most of my samples from virustotal.com, which, if you're unfamiliar, is a website which allows you to upload any file and scan it with something like 65 antivirus products. And they can tell you how malicious this document or this file or this URL appear to be. Now, I downloaded about 500,000, but only was able to use about 160,000 samples. Everything was fast, relatively easy, and relatively well labeled. However, it wasn't perfect. Here you can see this document that was labeled as a macro document, but when upon further inspection was actually just an empty Word document, contained no macros at all. So not everything was perfect, but it was fast and convenient. In terms of features, I did do what most people might think, which is look at file names, or look at the entropy of variable names, or the entropy of function names, or the number of functions in a file, or the entropy of the whole file. But more so, I used 800 interesting language and keywords. And I counted those. So basically the frequency of those words in the document, but I also used the term frequency inverse document frequency. Basically, how rare are these keywords? So here's an example of what that keyword count and term frequency inverse document frequency would look like. Here we have the word or the string file name. Now the count for this document is 3. And while that feature is important, the most important is the term frequency inverse document frequency of the string file name in this malicious macro document. The code for doing this is relatively simple and is on the screen here, along with a vocabulary sample on the right. Now I did avoid a number of features. So the OLE VBA library that I built this project off of, or Object Linking and Embedding Visual Basic Application language, did have a number of features that I could have keyed on. It had a number of signatures. While I avoided these in the beginning, I think I should have gone with them later on. Base 64 or a hex string or just a simple signature for the Drydex malware would have been a good thing to pick up on. But I wanted to focus on only the source code because it's easy to bypass signatures like this and because the model is based on source code. And if I really wanted to dig into this, I could have gotten into trying to find or detect VBA stomping and account for that. Basically, Visual Basic bytecode can be executed and is stored in the document just by itself. The source code for that doesn't necessarily have to be there. And sometimes threat actors will delete the source code, but the bytecode is still there, or they'll mess with the bytecode while leaving benign, innocent source code. And so here we can have a message box to say ABC, but when the bytecode is edited, it can be made to say XYZ. For more information, you can see this link below. But if I wanted to even widen the scope beyond that, I could have looked at the document metadata, like looking at page count, word count, authorship, timestamps, and lots of other metadata. And I decided not to go down that hole and just really focus Another feature I chose not to key in on was the size of the documents. Here you can see a distribution of all the malicious documents I downloaded in terms of size. And I figured since most documents would be under 10 megabytes to fit through the most email gateways, I decided to just cut it off at 10 megabytes. As you can see, the size of malicious documents and benign documents are mostly the same. So the distribution was fairly even and I wouldn't be able to use it as a good indicator. I decided to go with sklearn's random forest classifier. I used 100 estimators with a max feature set of 0.2. In all of my testing, with a 30 or 20% split on test versus real data, training data, I always scored above a 99%. But I did experiment with several other forest sizes, or changing the number of estimators or decision trees. And while technically they did test better, they ended up doing more poorly because they were more prone to overfitting to all of my test data. And we'll get into that a bit later. But knowing that all of the decision trees were doing well, all the cross-validation scores for all the trees and all the different configurations still stayed above 99% as long as I was using at least 100 decision trees or estimators. And I did so over 1,600 features, about 800 of those vocabulary words that we might talk about in just a minute. Overall, we had 110,000 malicious samples and 50,000 benign samples for files that we could actually extract the VBA for reliably. Overall, the newer model did much better, as one does with 80 times the data. It was faster and it was more confident, but the confidence varied more. I did test, like I said, up to 500 trees, but it would start calling everything malicious. Here we can see that the larger the sample size, the better the data we got. Here we got 10, 100, and 20,000 samples for both benign and malicious each. But I decided to oversample on the malicious documents so I could better detect those. Unfortunately, at 20,000 documents each, I still saw some fluctuation in the most important of all the features, and I decided that more data was needed. So I scaled it up to 160,000 samples in total. There was less variation in the most important of the features, and you can pause the video here if you want to examine them further. But I decided to train the final model on all the training data. All in all, I collected and trained on about 81 gigabytes of documents, which led to about 2,000 megs of features, just raw features, in terms of data frame written straight to disk, and a 20 meg model. While my model performed better than the old one, there was more variable fluctuation in the confidence level over multiple runs. For real-world testing, I decided to download documents from VirusTotal that had 1 detection, 2 detections, 3 detections, so on and so forth. The old model predicted them all as benign, and my new model successfully classified many of them as malicious. Here's a visual representation of that. Here we have the number of VirusTotal detections versus the confidence of the maliciousness of those documents. You can see here, several of them were mostly classified as blue, as benign, which is good. And the entire time there was a cross-validation score of 99. And most importantly, the most malicious documents, or the most obviously malicious documents, were classified as malicious. There were several challenges. The data was very biased, and it didn't have perfect labeling, and I accidentally deleted a lot of the data at one point. And it was expensive to acquire, and I did fill up my hard drive. So I did switch to an external hard drive, and I did I put a band in the documents that I was collecting from 2016 to 2023 to give antivirus companies a way, or at least a chance, at least a year to classify many of those very malicious documents. Real-world applications can see this model be installed in numerous places, wherever there's documents, really. And I've also ported this to PowerShell. Thank you.